I'm back from lunch, short break, but hopefully reinvigorating. And so we'll start off the afternoon session with Enrique.
Okay. Thank you again for the organizers to invite me. It's a pleasure to be here. So I think this is like a good follow-up talk from the previous one. So they did an amazing job introducing all these models and all the challenges there in power systems in terms of stability and other things. I guess like the question that I'm going to try to give some point of view is something that, since I started working on power systems, sort of like puzzle me. This notion that you want to emulate inertia and make the system heavier to actually control it better. And from the control theory point of view, it's a little intuitive. And I hope that now I can give like a partial answer explaining why we might as well try to do different things beyond like just naively virtual inertia. And perhaps the takeaway and things that I hope that you can get from the talk is like, number one is that low inertia is not necessarily a bad thing. And number two, if you embrace low inertia, then there are things to do beyond virtual inertia that could be much better. And I'm going to just show a few examples of how to do that. So of course, like this work with my student and collaborators, Fernando Paganini from the Universidad de Uruguay, Richard Pace, Lund University, and Jiang, which has done most of like the mathematical work. Okay, and of course, like acknowledge to all the agencies. Okay, so let's go back from the beginnings in a more like stylized way. So frequency control in particular, since the beginning has been centered around like generators, making sure that generators keep like a certain steady state speed, which is actually proportional to the frequency. And one of the core components of that is this particular Droop control, which it appears right at the beginning, and it's been in the 1900s, and we still use it today. And it actually came from long before that, like in the 1700s. It was already used in steam engines. So this idea of actually measuring the speed and actuating according to that, and it's essentially from the control point of view what we call negative feedback. So if you see like the frequency going up, then you essentially like you're going to actually go down on the power that you give. So higher frequency, lower power. It's a basic idea, and the reason I think like why it's this still there and it's being used is because like it works really well, and it also embraces like how like synchronous generator works. So this is like usually when you talk about frequency control, you see like this balance between demand and supply. So I'd like to give like a more precise version of this. So you could think of the length of these arms as actually inversely proportional to the inertia, and also I think of like this way, this counterbalance, as like these frequency-dependent loads. So what happens is that when you have like more demand than supply, then there's an imbalance. This imbalance is actually projected on a different frequency. And if you put Droop control like on the generation side, well, what you do is just you put more weight here, and you control the frequency like tighter and tighter. Okay. Now the problem is like we all know there's like a dynamic degradation happening. We see everywhere like we've seen talks talking about like Ireland, one of the cases that you actually have like this limited amount of renewables you can integrate, like Northern system and Nordic system in Europe, and even the United States. Like there's concerns of actually like frequency performance becoming like worse and worse over time. So what's the reason for this? Well, arguably you can say like sure, like the inertia is becoming smaller in the system. Secondly, there's a lot of power electronics connected, so there's a lot of like these frequency-dependent loads that used to be in the system that are no longer there, or they're diminishing. And finally, like there's like lack of service. So this is sort of like similar to what Lina was showing. So in the case of like the Eastern interconnection, so they did like this survey of trying to understand how many people were implementing Droop control in their generators, and well, many disable it because actually it deteriorates the generators. But most of them actually either didn't respond or they didn't know what was actually being said. And only 30% actually had some sort of threshold, and the threshold was pretty bad. And only 10% actually was doing something continuous in time, like sustained Droop control. So when you put all these things together, then this is how I look at the picture. So it's lighter, it's more sensitive, and also you have like less weight here for counterbalance. So you have frequency fluctuations that are larger. Okay. So the point is that this has been acknowledged, and there's even in the United States, like the FERC actually is mandating new renewable generation of medium size and large size to actually to provide some frequency response. Which brings the question of like how should we actually implement frequency response on systems that actually don't have inertia. So I think like there are many challenges in doing this. In particular, measurements. So you need to measure the frequency to actually implement some action. So that means that you have delays and you have noise. I have had some work on both of them. I'm going to talk mostly today about the noise. There's a question of stability and robustness, and David talked a lot about this. I'm going to talk less about this today, but more about performance. And there's also like this, what I call like lack of incentives. Like nobody wants to do it because there's a cost of doing this. And I'm going to show you what is the cost. It's going to become clear. So what is the current approach to do this? Well, as I said, like virtual inertia, everybody heard about that. So, and you can think of virtual inertia saying, okay, so I have this very fast converter, and actually make it mimic like with a controller this old system. I think like the telecom analogy I usually give is like it's kind of like having your iPhone and making it work like an old phone. Sure, it's gonna work, but that doesn't mean it's like the best way of doing it. And I hope that I will provide like some convincing arguments that there are more things that you can do. Okay. Okay. And the hope is that I'm gonna show is that like a systematic procedure by quantifying performance and realizing what are the key parameters that affect performance in the system, and then also use this performance quantification to design controllers that actually can improve in the performance quantities that I mentioned before. And these controllers actually going to significantly look, well, cool, that not necessarily are related to inertia or virtual inertia, okay? So what do we want to do? Exploit the fast capabilities of power electronics, improve dynamic performance, so minimize control effort. And this is going to be like a key topic, control effort, and the control effort that is needed to actually implement these controllers. And then the stability and robustness, okay? And as I mentioned before, I'm going to make some comments on the end about this. Okay, so I figure like the best way to understand the things is, and since if you are in like the Newton Institute is actually trying to think of like a very simple system, like a pendulum, and try to understand what happens when you have high and low inertia in the system. So first of all, like I like to write it like this, and now you see like inertia, how it appears like down here, and it's this way of actually making the system like accelerate slower. The big difference with power system was say like usually we have like a 1 over m here, but for the pendulum you happen not to have it, but close enough. And by the way, this is the same picture as like here. I didn't know that. Okay, so but let's try to gain some intuition about this with a pendulum. And I hope you'll realize that there are pros and cons with virtual inertia, with inertia. Okay, so it's like a pendulum, heavy. And what I'm going to do is actually going to put a force here, and I'm going to try to push it. So these are forces, friction, and actually the exogenous force in red, and then we have angle and velocity. And what you see is that you have like a very strong force, but because of the inertia, the deviations from the steady states are not long. But on the other side, it takes quite a bit of time to actually to settle back down. Now, let's look at what happens. Okay, so what is the idea? Is like it provides like this natural disturbance rejection, which is nice and something that power system engineers have used a lot. But also it's like, it has this annoying problem that it's actually hard to go back to steady state. So sure, it's hard to move, but if you move it, then it's going to take a while to come back. Okay? What about like a low inertia pendulum? With the same friction, it's just changed the amount of inertia that the system has. The same force. Now, the oscillations are larger. But I hope like you can see that this actually tends to converge faster. In fact, like it's already settled here. Last time it was around here that I ended up setting it down. Okay, so it's susceptible to disturbances. If you move it, it's going to move around more, but then it settles down faster. Okay, it regains steady state faster. Okay, so of course this is a pendulum and it's not like a real power system, but I hope that by doing these 3 steps, I can actually convince you that a similar thing is expected to be seen in the power systems. Okay, and I call it this roadmap to low inertia frequency control. So I'm going to first define performance metrics that I think like capture the different type of dynamic degradations that you have in the system. Then I'm going to quantify it in stylized models how these performance metrics depend on the different parameters of the actual system, inertia damping, and like your controller, virtual inertial Droop control. And I'm going to show some limits, some limitations that you have when you do this with virtual inertial Droop control. And at the end, I'm going to show that by just doing something slightly more sophisticated, not too much for the control theory point of view, then you can actually improve if you want in all these different metrics. Okay. Then feel free to ask any questions at any time. Okay, so the best way to quantify performance is like to look at how the system really behaves. So what I'm showing here is frequency, evolution of frequency over time. And this is like an event that happened in San Diego. So what we see here is like different places that actually have different measurements of the frequency. We see these fluctuations. There's an aggregate value over here. And then suddenly San Diego gets disconnected. There's a blackout. And then you see like the whole frequency is going up, but also you see like these like waves going up and down. And like this is very common. So I want to comment on 2 things. Number one is like the time scale. It's like this is real time, so it's actually it's quite fast, but not really fast compared with like, power electronics. And yeah, and the second thing is that you see like these huge ups and downs, fluctuations, and like these inter-area oscillations that happen in the whole system. Okay, and all of this depends on network, the type of disturbance, like the generator models, and many other things that I'm not even going to discuss. Another example. This case was like a line tripping. Again, fluctuations of frequency at different parts going up and down in different places, but the average frequency seems to stay very the same. That's because like you didn't lose like an entire city of demand. It was just a line. Okay. So the hope is like that good performance metrics actually must identify and quantify like what are the sources of these degradations and these different phenomena. Okay. So this is like my summary of what I see of power engineering metrics. So this is the first one you see for frequency control. It's like you have like the rock-off, you actually have this nadir point, the lowest point, and then the settling point. They call it point A, B, and C. And arguably these are important in the sense that we have like this under frequency low shadings, and you go beyond that, then you disconnect things. So you want to make sure that you satisfy those things. Yeah, and on the other side, like you also have like this like eigenvalue analysis based on dominant modes, trying to understand what is like the dominant damping of the system and these type of things. And you can loosely connect it to like the network and like modes of the network. So my point is like these are things that are really good at capturing like the system degradation. So the degradation goes low, then either you see a problem here or you see a problem here. But they're not really good at quantifying the sensitivity. In particular, like how bad it is like you have like 2 or 3 dominant modes, and how do they depend on like inertia, damping. We have some idea that is related to the network. I have not seen like a really convincing like argument of like exactly how this depends on all the parameters of the system. Okay. On the other side, like, we have like the control community that have been working on like these system norms, trying to quantify performance. And the idea is like, well, you put either deltas of stochastic white noise on the system, and then you measure the output, and then you look at things like, okay, functions, like quadratic functions of the frequency, so coherence, how like the phases move away from the common angle, or like losses. It's like a ton of work on this, and many people are here, like Denise, Florian, John. I'm sure I'm not missing anybody. So a lot of people have been working on this type of things. And I think that, and then you can define things like, so like infinity norm, so like maximum values here, or L2 norm, and like integrate like quadratic of the square of the outputs over time. You can use this as your metrics, and you can get like in many like ideal cases closed form solutions. It's really nice, I think, for qualitative analysis. But the assumptions are like very restrictive at this point, I believe. But it's also nice to get like some computational methods out of it. So anyways, like, it's still like I think that there's these connections between Nadir, Rokov, and even step disturbances. So these models so far didn't, or most of them did not cover like step disturbances, which is when you disconnect like a demand or something like that. Okay. So here's like my attempt to put the things together, connect power engineering with like system theoretic tools. For step disturbances, what I'm going to do is look at, this is the frequency of a bus, and I'm going to separate it in 2 parts. So I'm going to get the frequency of all the buses and do this weighted averaging, and this is not new. So you go like Contour, then this is called center of inertia and very well known. So I'm going to use this as what I'm going to call the system frequency, and I'm going to decouple that component from the rest. So there's going to be an error, a synchronization error, that is essentially the frequency of a bus minus the system frequency, this weighted average of the frequencies. Okay, and we're going to use the system frequency to define all these metrics that we mentioned before. Rokov, Nadir, steady state. And by the way, we can put them actually in the nice formulations that I said before. So, so the Nadir is like the largest deviation of the system frequency. The Rokov is the largest deviation of the derivative of the system frequency. And then I'm going to also use the steady state effort as a measure of like how much effort I need to bring the system to a particular steady state. And this is going to be in the context of like inverters or the controls that we're going to use. And on the other side, we're going to have from the deviation from this mean frequency, we're going to measure like the area square, and we're going to call this synchronization cost. Okay. So this is it for frequencies. What about stochastic disturbances? Again, I'm just going to assume that there's some noise. There's like demand variations. That means like the system is never in steady state, but we still want to make sure that that the frequency variations are contained. And then we have these measurement noise that I mentioned before that come from the inverters. And you can measure the variance of the steady state variance of this process. Okay, and it's the H2 norm of a well-defined system for those of you that are in the control side. But if not, think of this as a variance. Okay. Okay, this is the full setup. So we have Rokov, Nadir, steady state effort, all based on this weighted average steady state system frequency, and then variances of like frequency deviation from the nominal. based on stochastic disturbances and measurement noise. Okay, so can we use that to quantify like performance, so give essentially numbers based on the different parameters of the system? And I'm going to do that on a stylized model. I'm glad that David gave his talk, and he first explained everything that is wrong of a model like that, but then also he stated, well, there's a value of starting to analyze the things in this case. So I'm going to go in that part and I'm going to say there's a value of analyzing this in this case. And sure, like there's a lot of other things that you could consider, but I would argue that also that many of those for like the time scales that I'm mentioning are not necessarily related for frequency control. So what is the model? So it's like the node dynamics, as was mentioned in the previous talk. So I have like individual buses here, the nodes of your network, and these are some dynamics that go from a certain power imbalance to frequency. And then we have the Laplacian, as in the previous talk, that it's like some sensitivity or linearization of the power flow equation. So I'm using actually a linearized version of like the swing equations and a little bit more, and I'm going to say exactly what I'm going to do. And then I have like these step disturbances. So in control, we usually say step disturbances is 1 over s, like of like a Laplace transform. And u is essentially the vector of the directions of the disturbances, and the stochastic disturbances that I mentioned before. So I'm going to do specific formulations here for each one of the bus dynamics, and essentially, I'm going to consider 2 types of like generator models here. The one is the standard swing equations. So here's the inertia, the acceleration versus the imbalance, the damping term, and this is like the net imbalance coming to the generator. But I'm also going to consider like a system with a first order model for the turbine. And I'm going to show the difference when you start to like systematically quantify the performance, how like these 2 things, the first order, they do matter. For the inverter, I'm going to just assume like a flexibility in the design, meaning that I can actually map frequency to power. I'm not actually modeling like the fast dynamics, and arguably for frequency control, all the fast dynamics will be solved before. And then I'm going to consider like these models that I mentioned of like Droop control, so this negative feedback proportional, and then which like in the frequency domain is just like a flat curve, that meaning that any sinusoid that gets in gets multiplied by this value, no matter the frequency. In virtual inertia, essentially, it has a similar behavior, but eventually, like high frequency starts to amplify more and more, and this is because of this derivative term, like derivative with respect to time that you get on virtual inertia. So these are my models, and once you put it in the loop, then you can see why, in a simplified stylized model, why we call this red virtual inertia, because essentially it adds mass, and why we call this like a Droop control, because essentially it adds to the damping. And because inverters are fast, it doesn't go through the turbine. Any questions about this model? Oh, okay. So let's go back to our pendulum. Yeah, so this is the case that I mentioned before, low inertia pendulum, and high disturbances in amplitude, but it settles fast. So this is what happens when you add inertia to the pendulum. So what we do is we add like this additional term that essentially is going to amplify the M here. And I'm also going to show the control effort of doing something like this. If it starts. Okay. So first of all, like, well, you see, like the control effort of actually mimicking the mass of this heavy thing is actually high, and also like at a certain point, it seems like a little bit useless. In the sense that you're still moving, but you are the one that perturbing the system with the inertia that you're adding. So you are like continue moving it for no particular reason. So provides like good disturbance protection. Arguably, this is fine. I agree. But also, like it still is hard to regain steady state, and the control effort is pretty high. So let's see what happens if instead of that you increase the friction for the same system, low inertia. So it's much faster, and the reason is because like this is like something very light. So if you add like something very light, some friction, then it's going to settle down faster. So the whole knowledge of adding large inertia to make the system heavy, it has advantages, but it also has a lot of disadvantages, and we have to be aware of those things. Okay. So I think like if you have to choose one of them, I will go for damping and for this friction. And for this model, there's no cons, I think. Let's see what happens in the actual system. Okay. So what we're going to go is actually do the same analysis based on all these performance metrics that I had over here. And to do that, I'm actually going to make an assumption. So it's going to be a stylized analysis, meaning that what I'm going to assume is essentially that the transfer functions of your machines are proportional to each other, where this Fi is essentially the relative inertia of each generator, of each pass. Okay? So you pick the maximum inertia, and you essentially you use that to divide every other one, and then there's going to be one that is 1, and then the other ones are going to be smaller than 1. And then I'm going to assume that my controllers also satisfy a certain proportionality assumption in the transfer function. So for the models that I mentioned before of the swing equations and the swing equation with turbines, this is like this like a uniform damping ratio type of assumption, together with an additional like uniform turbines. Not a good model, like in the sense of there's still some restrictions on this, but when you see like the statistics, they're not necessarily that bad, in the sense like flat here means that this is satisfied, and here you go from 0 to 1500, and here from 0 to 15. So it's just an approximation, okay? And then, like, again, this also implies that it has some proportionality assumptions in your virtual inertia controller. Okay, so how are we doing with time?
A little bit now. I don't know. You started 10 minutes late. So.
10 minutes, okay, so half an hour. Okay, good. Yeah, 25 minutes. So what I'm going to do is actually I'm going to take this model, and under this assumption, we can make a change of variable depending on these FIs that appears here. And we sort of like end up decoupling the system in n subsystems. So each of n subsystems essentially has this idealized model of like sorry, here it should be a G, not a P, of the generators. And this is essentially the controller. There's this additional lambda that is essentially one of the eigenvalues of the Laplacian, a weighted Laplacian. Actually, yeah, it's the weighted Laplacian multiplied by the inverse of the square root of the inertia. Yeah, similar to the one I had in the 1981 paper of David. Okay, so and the point is like when you do this, then these subsystems are actually of small order, and we can actually compute things here. Okay. And there's similar work has been done for the case of like uniform parameters, but arguably this is like a better assumption in the sense that you assume there are proportional parameters with inertia, so you account for like large variance in the size of this system. Okay, and the first mode that has a 0 because there's a 0 eigenvalue in the Laplacian, it's actually related to the system frequency that I mentioned before. And the remaining modes that depend on the lambda actually affects the synchronization error. So you see like already that the network is captured by synchronization error, and the response to aggregate disturbance is going to be captured by the system frequency. So it's a nice decoupling that happened under these assumptions, but we have other ways to still look at similar results in generalized cases. I can mention that if you're interested. Okay, what about step disturbances here? So this is the same diagonalization that I had before. So you put an input on some direction, and then you essentially measure the output. And these guys have like an ugly form, but the point is it depends on your controller and the generators and the lambda case that you have over there. Okay, it's an ugly. All I want to say is that once you do that, then you end up having like one frequency that is the same for all the buses, and another frequency in another like set of like dynamics that actually depends on the input response of this guy. So some functions of time that appear. Okay, and these are actually decoupled, and you can measure these things separately. So this defines the synchronization error as a function of the properties of the system. So what can we say? If you look at the swing equation model, and you look at the system frequency, then we can analytically compute the Rokov, and we can say that actually depends as 1 over m. Arguably, this is not something not extremely new. But the interesting thing is like when you just use like system inertia, then swing equation, sorry, then you don't have an overshoot. So actually, the steady state value is the nadir. And the reason is because like you're missing like the delayed response of the turbines, and that's the one that generates that. So arguably, like for the control community that has been used models without the turbines, I will argue that if you're looking at step disturbances, then it's important to have the turbines there. Okay, so the model does not match the empirical observations. So we can compute the same things after a lot of work for like the case with turbines, and again we can do the analysis and something that is not like as trivial as before, but still can show that this Rokov depends with 1 over m, nothing fancy there. There's a steady state that depends on the droop of the turbine, the damping, again, nothing new, all the things people knew it. And we also can compute, you can see all of it, this ugly expression for the nadir. That depends on a lot of parameters here, but the inertia is here, the damping, the droop control of the turbine, everything is there. But the interesting thing is like now we can actually look at the sensitivity with respect to that. So is it better to move M or D or R? And that's what we do. Essentially, we plot the nadir with respect to damping and inertia. So the colors here explain different inertia values, and they vary like in 4 orders of magnitude. Now, the nadir actually happens to have like very little effect. So the inertia changes the nadir, but depending on the system, the effect is like not significant. And it depends really on how much damping you have in the system, whether this is like a big issue or not. When you look at the nadir now in terms of like the turbine droop or the turbine time constant, then again, like you see that for different time constants, then there's not necessarily like a measured change, and it really depends on like the amount of like turbine that you put in. So I guess the point I want to make is that like the damping here seems to be the one that gives you like a better response, and surely if you have like a higher droop gain on the turbine and the turbine is faster, then you can get similar response than the one that you had in the damping case. Okay, and the red dot is the nominal case that we have. Okay, so ugly picture. Now I add like this virtual inertia, and you just add like additional terms here, but again it essentially changes the mass and the droop of the damping of the system. I just want to like show like a simple case of like also the steady state effort. So it's essentially the amount of effort that now like the inverters need to put to implement these controllers. So this is a system without control. So the virtual inertia coefficient and the Droop are 0. There's no control, and there's like some given like response. If you increase the inertia, the virtual inertia, sure you improve the Rokov and the nadir, but you have like quite a big of like effort needed to do that, especially at the beginning. So changing the Rokov, it requires you like high consumption of control. So essentially you need to input a lot of power to make sure that the generator does not go so fast. And for the Droop, well, the maximum power is less, but you still have like this steady state effort that you need to put to maintain the frequency like in a different value from the value that you will get from the turbines. Okay, so this is for like the system frequency. We have a similar story for the synchronization cost. I would say it's a little bit more uglier, and the whole point I want to make is that we can't compute this, and it depends on two parts, like depends this matrix Y, that depends on two terms. One that actually depends on the eigenvectors of your Laplacian, that is on the network and the inertia. Another one that depends on the dynamics of your system. And we can compute this measure, and there's a DC series related to the direction that you make the perturbation, and we can also do an average over like different disturbances if you want. Now, I think like for the sake of time, I'm gonna not go through detail like on the swing dynamics case and the computation for the turbine. So, but let me just say the following: that what we see from the numerical, like this analysis, is that in general, like change in inertia, it gives you finite values of synchronization cost for any value of the inertia that you put. And I think this is better explained. And secondly, it's like if you want to make the system synchronize faster, then damping is actually the right answer. So D here, if you increase damping, then you decrease synchronization cost. So these flat lines are essentially inertia. So you change inertia, and you're not going to change the synchronization cost. So why is that? Well, here I'm just having like these oscillations. I'm showing it for changes in the parameters D, R, the turbines, and the mass of the generator. And this is the nominal system. The reason is because the oscillation stays longer with larger mass. So here, surely, you converge faster with higher amplitude. And here, actually, the oscillations become like with lower amplitude and and longer. And damping, well, you still have some slightly benefit, almost nothing in terms of like the worst case, but you very fast like converge to the right value. So this decreases the synchronization cost significantly. And all the other ones, these numbers are basically the same. Okay, so damping is the one that actually helps for the synchronization cost. What is more interesting is actually the control effort that you need to implement this Droop control and the virtual inertia in this case. In particular, virtual inertia gives you huge control efforts, and this is again the same thing that we saw with the pendulum. It's like this is essentially the virtual inertia pushing the system to the sides for no particular reason, and we can see it. And this is an order of magnitude larger than here. Okay. But so notice that I tuned this so that the system response is actually critically damped. You could argue that this is probably too much, but I'm going to argue that I can do something very similar to this and get a response that is essentially critically damped. And I'm going to go through that in a second. Okay, so about stochastic disturbances, let me just mention that we can compute them in a similar way. They have an ugly form, but the point I want to make is that you can improve the stochastic disturbances at a certain point using like your Droop control. It depends like on the inertia too, and on the true inertia of the system. But it also affects the steady state effort. So if you want to dump more, if you have a step change, then you're going to have like a large steady state. So there's a trade-off there. And what about virtual inertia? Well, if you don't put any filter, then it just amplifies the noise everywhere. Okay, so for measurement noise and for synchronization error, virtual inertia doesn't seem to be like a great idea. Okay, so I'm gonna take like the last 10 minutes or so, if that's, yeah, we're still fine, to actually show like a very simple way to improving these things. So the idea so far is that sure, like virtual inertia can help with the rock of a nadir, but it's bad for synchronization costs. And Droop control actually seems to do things pretty well, except that it needs to increase like the steady state effort for quite a bit. What about like this new solution? Well, so this is like what we do. And again, I'm not saying this should be the final solution. I'm just saying that this is enough to improve in many things. You take the virtual inertia that you had before, and that had this like type of like frequency dependent gain, and you integrate it. So essentially, yeah, you integrate this term and you add like a stable, what we call like a stable pole, like a filter, you can call it. And this additional degree of freedom is going to be actually very helpful. In particular, you can get things like different gains. You avoid this like large amplification that was the one that gives you the noise. But also, like you can have different gains for like the steady state, which is what Droop had to commit in a step change, and the one that you use for like your dynamic performance. And you can work it as a lead or a lag. That's our term that we use in control. So what happens when we go through all these different things? What about like the system frequency? So again, this is as before, like we have like this second order response. What we can show is actually for this model, and this is simplified analysis, then we can completely cancel the nadir in a different way, that it doesn't need to add a lot of inertia to the system to do it. And it's by tuning the parameters of your system in a particular way. When you do that, then you get like a first order response. And the idea is very simple. It's like you look at the main mode, the one that defines the system frequency, and you have like your generator, you have like turbine, and then you have like this control. So this tuning of parameters essentially does the following. So that's a control that it puts like just like these constant gains and subtract the effect of the turbine. So the idea is like nadir comes from the turbine actually having delay. So we can use the turbine to essentially, you can use these faster controllers to counteract this bad effect of the nadir and still end up with a system that is much simpler and responds faster and does not have any nadir. We can also look at synchronization cost, and the only thing I want you to remember is like this Y matrix that defines the synchronization cost depends on these products. Each element of the matrix has a product like this. So what we can show is that if you tune the parameters in a different way, this actually becomes 0. So the synchronization cost can become 0. I'm not saying this is what you should do. I'm just saying that this is achievable. Before, for virtual inertia, the synchronization cost was always constant. Here is not the case. And these are parameters that do not affect the steady state of the control effort of your controller. So we can kill completely the synchronization cost if we wanted to, in an ideal case. And there's a similar story about stochastic disturbances. You can essentially tune differently, like how to actually, there's an optimal value to optimize your noise amplification in the system. We can compute that, and we can do that without actually changing the steady state effort of your controller. So you can tune this, yeah. So arguably, I think that this is also like, in a sense, better than the two things. But let's look at a system that actually has low inertia, like the Icelandic power grid. So what I'm going to do is actually I'm going to introduce the, step changes and stochastic disturbances to the grid, and look at how these different controllers work. This is the zero nadir, the zero nadir tuning that I mentioned before, the one that cancels the effect of the turbine. So essentially, instead of having this overshoot, then you just have like an average of first order response. And it's faster than what you will get if you use large virtual inertia to get this critically damped like response. But more importantly, the control effort is not drastically different than through control. So you can remove this overshoot with necessarily not too much additional control effort. If you look at stochastic disturbances, then the PDF of like our iDroop is here and the other ones are here. Again, this is idealized scenarios with some of the models, but we are actually looking forward to test this in more realistic systems. And our belief is actually similar tuning can be generalized in many of these cases, but the one thing that is true is like this case is with heterogeneous parameters. We don't assume the simulation proportional parameters as we said before. And we can also like do the two things at the same time. We want to optimize for steps and stochastic disturbances. So there's a trade-off here. So if you mitigate too much the disturbances of stochastic disturbances, then you become slow. But you can still manage to get like a first order response without major effort and without any significant, actually, reduction in variance. So I think I'm gonna wrap up here. So what I present is like a stylized system in which we try to understand what is the role of inertia, what is the role of damping, and the role of different controllers to actuate in this system. We define these metrics, and we were able to compute in some rather generalized case of like proportional parameters. And we compare all these different parameters and see how they affected the performance of the system. And I think like the takeaway message is like, number one is like model matters. Like if you have step disturbances, the swing model alone clearly is not important. And I'm sure for power engineers, then it's like, yeah, I agree. So I think that this idea that like low inertia is something bad, it's arguably not necessarily true. And there is intuition of if you have a system that is lighter, sure, disturbances are gonna perturb it more, but it's also easier to control. Think of like having like what is the engine that you have in your car versus a truck. It's much larger. So the effort needed to control a system with lower inertia should be smaller than one with large inertia. If I have to choose a term between inertia and damping to control, I would use definitely damping. And I feel like if you are able to do more flexibility things, then I hope I show that there's a lot of things you can do that actually improves before like trivial like Droop control and virtual inertia. So this is like not a complete story, of course. Then there's a lot of issues still around. I think there's a lot of research important in terms of like making sure that the faster time scale are actually stable. But my final point is that given that you stabilize the faster time scale in the connection between converters and the voltage regulators, then the slower time scale should be able to control it very, very well without major control effort from the inverters. And that's the final message. So thank you, and if there's any question I've got to answer. Yeah.
Questions?
The videos in the beginning and the animations in the beginning showing the not the frequency or is it the phase?
Both of them were
moving up and down. I mean, I can imagine one of your friends at Caltech, getting scared about stiffening that waterbed too much. Maybe somehow it breaks. I'd love to look at like one of these PD models of the West Interconnect and see what happens when you make it too good. But locally, it's very fast and responsive. But if something goes wrong in the, I don't know. It sounds fragile if you make it too.
You say like it sounds fragile if you just use dumping.
If you make the whole West Interconnect too quick, it seems like this tension got to break. Yeah.
That's what let me just put it this way actually. Yeah, and this is this point like
effects are fascinating.
I think like at certain point the faster time scales like become like important. The tuning that I'm doing is actually in the frequency domain of the response of the turbines and the generators. So the control action that I'm doing is at that level. So I'm just saying that the higher frequencies need to be handled correctly, and there's a lot of issues modeling the voltage dynamics and delays that you can have in that part. So sure, like there's some issues that are going to appear at the higher frequencies, but I think like for the frequencies that is the natural response of the turbine, then as long as you inject the right amount of power, then you can control it. That's my message. Yeah. I think like on the other part is like delays, like voltage stability, all these other issues are going to be important. But for power and frequency control, then just like make sure that your inverter is given the certain amount of power at a certain amount of time, depending on your system, and you should be able to control the generators. Yeah, that's only what I'm saying. Yeah.
In the Icelandic case, you have lots of hydro, I guess, with reservoirs and pipes, and they have a non-phase minimum behavior. I think it's kind of turbines. Does it change anything?
I saw those things. I have not modeled those things in my simulations. I also know that there are some controls that are designed to essentially cancel those non-minimum phase behaviors that I've seen used, and it's actually very similar to the one I used to cancel the nadir. I'm not sure exactly how it's really implemented at that point. Since I have like very simple models, and that's why I say like we need to look at more complicated models of the system. Sure, yeah, but again, I guess like from the control point of view, it's a question of like what time scale we're talking about. I think for the time scale of like this response that we saw in the initial figures, you should be able to set your inverters to provide the right amount of power, and making sure that the fast time scale this is stable. And there's a lot of research, a lot of people working on this thing. Florian is working in like interfacing inverters, and Cyrus Doppel is also working on interconnecting inverters with generators. And I think all these things are very important. I am not making any claims about that time scale. Yeah.
Often practitioners tackle to these problems is switching controller. Like you have initially only inertia, you make yourself heavy, and disturbance strikes, and then you put all your money on damping after say 1 second. Did you think about such heuristics?
I actually that's so what is the reason to do that? Like the Rokov? So I don't know if Rokov is such an important metric, to be honest. Maybe like more expert power engineers can tell me, but my understanding of Rokov is that the only reason why you measure Rokov is because your turbines have delay, and therefore like high Rokov plus delay of the turbine gives you big nadir. And of course there are other issues related to like the acceleration and the torques that you put in your generators. But now if you have a generator that is like lighter, then I don't see this being such a big issue that it was for a very big generator that if you put a high torque on the opposite direction, it's gonna twist it. And so I think actually Rokov is the reason why Ireland had some limits, and that was actually changed by redefining the things. I think if you're really interested in a measure, it should be frequency deviation up to a certain point, and surely you need to quantify better what is the effect on the generators. But based only in Rockoff, I'm not sure. As I said, maybe let me just show this thing. Yeah. So in this case, we actually have a Rockoff that is not changed, and is this something bad? I don't know. I'm not sure it's that bad. It just converges faster to the new steady state. So let me put it this way. I think we should rethink the role of Rockoff, in system with low inertia. Yeah.
I fully agree with that. Another maybe more mathematical reason would be if you split your control into proportional and derivative channel and plot the two time signals individually, you see actually nicely there's a bang-bang behavior, which indicates if you allow yourself time-varying switching control gains, maybe the optimum is actually a bang-bang control.
Depends on probably depends on what's the objective function of your. If it's linear, then probably maybe I still think that I think there's by the way, my tuning was based on an idealized model. We are now looking at models that are more realistic for this system frequency, and we can show that even in some cases there's not a finite state space. For big networks, there's a finite state space approximation for that. So there's a whole issue of how to model the true behavior, the system frequency, and how to tune to counteract that. Yeah.
Okay, I think we'll stop there.
Sure.
Thanks again.